Welcome back. In this video, we are going to be looking at calculations and questions coming from how a material deforms when you apply force. So if you've not looked at or if you've not seen the previous video where we derived and wrote down necessary formulas and equations, please do it to look at it before we start solving this problem. So let's look at this problem together. So it says, consider a 60 mm cube made of graphite reinforced polymer composite material that is subjected to a tensile force of 100 kilonewton. So let's write what we're given. So they mentioned a force. They gave us a force of 100 kilonewton. Now what is not anyhow force, it's a tensile force. So remember what we said in our video. In the video, our last video, we said that anytime you see a tensile force, you indicate it is a positive, a plus. Why if it's a compressive force, what do we use? We use a minus. So our force is 100 kilonewton plus. What is a compressive force? I'll put a minus 100 kilonewton. It's perpendicular to the fiber direction, directed along the what? True direction. Another thing you should note is whenever you are writing your parameters from this type of question, you must take note of where the force is being applied. Where the force is being applied. So here they told us that this 100 kilonewton is applied in the fiber direction. Do you remember what I said about fiber direction? Fiber direction is always direction 1. It is aligned with the fiber. Fiber direction or direction 1 is aligned with the fiber. So that they are telling us that this force is applied in the fiber direction. So my force, I'm going to indicate with a 1. Why am I putting 1? To show that it is applied in the fiber direction. If it's applied in the direction 2, I'll put 2 here. If it's applied in the thickness direction, I'll put 3 here. Just like that, depending on the question. Okay, so let's continue. It said it's directed along the 2 directions. So stop. The cube is free to expand or contract. Determine the changes in the 60 mm dimensions of the cube. So actually, I omitted the length because they told us that the length of the cube is 60 mm. So our length of the cube, that's the original length of the cube, is 60 mm. Now, the cube on its own has a length of 60 mm when it has not been, a force has not been applied to it. But when you apply a force, it will change. That's what we said. I want to predict that deformation, that changes in the material, in the composite material. Okay, so what they asked us to find, they said we should determine the changes in the 60 mm dimensions of the cube. The material constant for the graphite is, and they gave us all the constants. So they gave us E1 as 15.50. They gave us E2 equals to E3 as 12.10 GPa. They gave us Poisson ratio V23 as 0.458. They gave us Poisson ratio V13 equals to V13 0.248. This one don't have units. Then for shear modulus G23, it is 3.20 GPa, and G13 equals to G13 equals to 4.40 GPa. Now we are asked to find the changes in the 60 mm dimension. So we are asked to find changes in the 60 mm dimension. Remember, our coordinate system is 3. We use 1, 2, and 3 dimensions. So the changes, which is the length, change in length, is going to be in 3 places. Change in 2 and change in 3. So this is what we are asked to find. Now let's go back to our parameters that we have written down. Before we start to solve, let's make sure that all of them are in their standard units. So this is 100 kilonewton. I'll write it as 100 times 10 raised per 3 Newton. 60 millimeter, if you change it to meters, you have 0.06 meters. Then 15.155.0 GPa, that is 155 times 10 raised to power 9 Pascal. This is also 12.10 times 10 raised to power 9 Pascal. And same thing here, 3.20 times 10 raised to power 9 Pascal, 4.40 times 10 raised to power 9 Pascal. Okay, now if you observe in these parameters, there's something that is unique. We've said before that we have 4 types of, or 4 classes of materials. We have anisotropic, orthotropic, transversal isotropic, and isotropic. Now if you look closely at the constants, you will observe that this is transversal isotropic. Why? Because in transversal isotropic, our direction 2 and 3 have the same properties, like you're seeing here. 2 and 3 have the same properties, while fiber direction is unique. So E1 is unique, but 2 and 3 are having the same properties. So this is transversal isotropic material. Okay, so for us to solve, the first step that we're going to do is to, let's look at the cube. Remember, this is a cube that is of length 60 millimeters. So let's do a rough sketch of how the cube looks like. So our cube is like this. So this is how our cube looks like, and each of the length is 60 millimeters. That is 0.06 meters, and so on and so forth. So we know the size are 0.6 meters, and we know that in this cube we have three coordinate systems. So this is how our coordinate system is. If you remember, that was already in our last video. So we have direction 3, this is direction 1, this is direction 2. Okay, I didn't get this fiber direction where, so it's actually something going this way. This is direction 1. Yes, so this is my cube. Now, where did they tell us our force is being applied? They said our force is applied in the fiber direction. So in along the 2 direction, this is supposed to be 2. Along the 2, they said it is directed along the 2 direction. So it's actually 2. Sorry for the mix-up. So if you go to your cube, you have to try to draw the force, where the force is being applied. Remember, it's a tensile force which is pulling, right? So we can, and this is where our direction 2 is. So I can draw a line coming out. This is simply saying that the cube, we are pulling it out, we are stretching it. So the force that we are using here is F2 equals to what? 100 times 10 raised to 3 Newton. So sorry again, remember, if you look at it closely, they said that is subjected to a tensile force of 100 kN perpendicular to the fiber direction. They didn't stop there. They now say it's directed along the 2 directions. So statistically, they said now that it's along the 2 directions. So you have to go to the F2. So where I'm applying my force is in this 2 directions. You see the way the line is. That's where I'm going to put my own force, pulling out the tensile force. If it's directed along 1 direction, I'm supposed to draw it this way. If it's directed along the 3 direction, I'll put my arrow this way. So just take note of each of these forces, if it's tensile or compressive, and also if it's acting in the 1 direction, 2 direction, or 3 direction. Okay, so whenever you are solving this question, the first step is based on what we know. Remember, what are you looking for? You are looking for this change in dimension, right? You know that from our first equation, we said constitutive compliance matrix. We said that our strain is equal to the compliance matrix x times what? The stress. So if I'm looking for this guy, definitely my answer or what I'm looking for falls inside this epsilon, because I know my strain is mathematically change in L over original length. We wrote that formula before. So if I know this one, I can be able to find my change in L. So for me to be able to get this guy, I need to know this times this, then I'll be able to get this guy. After getting it, what do? I now make this change in L subject of formula. So that's what we are going to do. So we'll try to work it backwards. So for me to be able to know this times this, let's first get stress. So our step 1 is to calculate the applied stress. So where is our stress being applied? In direction 2. Okay, so what's the formula for stress? Remember, this type of stress, tensile and compressive, they fall under normal stress. So I'm using sigma in direction 2, and the formula is force over area. So my force in direction 2 divided by what? Area. This area is the cross-sectional area, the surface area. My F2 will be what? 100 times 10 raised to 3. What's my area? My area is the length times the length. So that's 0.06 times 0.06. So if you do this correctly, 27.78 times 10 raised to 6 Pascal. You know Pascal is similar with Newton per meter squared, so you can use anyone to write it. So I just used to leave mine in Pascal. So you have to 7.78 times 10 raised to 6 Pascal. Now, if I want to write, remember our aim is to do this times this. This one that is here is the vector form of my stress. If I want to write it in full, this vector form, if I write it in full, it is what? Sigma 1, sigma 2, sigma 3, shear stress 2, 3, shear stress 1 3 and shear stress 1 2. Please, if you've not seen the first video of this course, please make sure to see so that you can be able to understand how we got all this. So inside this shear stress, we have the normal stress part and the shear stress part. So this is simply equal to, now we have all these stresses, but our stress in this question is only applied to one particular place, and that is where? In the two direction. So every other guy is zero because no force is applied there for my question, and you can't have more than two forces applying on that material. It must be in one particular place. So either they mention one direction, that means the rest are zero. Three direction, that means the remaining ones are zero, just like that. So in this case we have two directions, and it is 27.78 times 10 raised to 6. The remaining ones are what? 0. So we have done our first step. We have gotten this vector form, which is this one. So let's go to the second step. The second step now is to get this compliance matrix S, to write the compliance matrix. Now if you remember, our compliance matrix is like this. This short S, if we explode it, if we expand what is in, is what? We have S11, and each of these S11, S12 have a formula. We've written that in our first video. It is 1 over E1, right? Then we have minus V12 over E1. We have minus V13 over E1. Then the remaining are 0. Here you have you have minus V12 over E1. You have 1 over E2. You have minus V23 over E2. The remaining are 0. Then you have minus V13 over E1. You have minus V23 over E2. You have 1 over E2. 0, 0, 0. You have 0, 0, 0, 1 over G23. 0, 0, 0, 0, 0, 0. 1 over G13. 0, 0, 0, 0, 0, 0. 1 over D12. Okay, so this is what our compliance matrix is with the formula. In our first video, we wrote it in a different way. We wrote here as minus V21 over E2. Then we wrote here as V12 over E1. We wrote here as V31 over E1. They are similar. Remember that we said there is a special relationship linking these two constants together. We call it reciprocity relation. So even if I don't want to use V12 over E1 here, I can still write it as V21 over E1 over E2, and it will give me the same answer. So for reciprocity, we said that V12 over E1 is similar with V21 over E2. We also said V13 over E1 is similar with V31 over E3, and V23 over E2 is same thing as V32 over E3. So this is what we said. So either you choose to use V12 over E1 here, or you replace it with V21 over E1, it will still give you the same thing. I just wanted to clarify that. So let's go back to the question. So after we have written our compliance matrix, let's do the calculations. We know what each of these are from our given data. So let's do the calculations. When we do that, we'll now put it back inside our matrix. So what's the first one? Our S11. S11 is what is here, the first term here. This is S12, S13, and so on. While here is S21, S23, just like that, like matrix. So S11 is what? 1 over E1. What's the formula? 1 over E1. What's the value? 155 times 10 raised to 9. So 155 times 10 raised to 9. Go to the next one. We do, I can choose to do all the Young modulus first. I can choose to do all these Young modulus first, then go to Poisson ratio, then shear modulus. So let's do the Young modulus first. S22 is 1 over E2. And this S22 is still the same thing as S33 because E2 and E3 are the same. So 1 over E2 is 1 divided by 12.10 times 10 raised to 9, which is the same thing as S33. So even if you want to say write S33 and put 1 over E3 and put the value of E3 there, the answer you get is still similar with 1 over E2 because they are the same thing. So S22, S33, S22 and S33, they are equal. Okay, so we are done with all the young modulus. Let's go to the Poisson ratio. See the Poisson ratios. These are the Poisson ratios. So for the Poisson ratios, I have S12. S12 is minus V12 over A1. What's minus V12 over A1? That is minus 0.248 divided by A1 is 155 times 10 raised power 9. And the value I get for S12, look at S12, is still similar with S21 because they are symmetric because of this relationship. So they are the same thing. So it's still the same thing with S21, right? So we have value for this, we have value for this. Then what about this one? Minus V13 over A1. That is S13 minus V13 over A1. What's minus V13? Here we have V13 is 0.248. It's even the same thing with S12. So, and the value you have here is still similar with what you have here. So S13 and S31, they are the same. So I believe we've touched all the components, all the elements here. So all the elements here, we've written their formula. So if you punch this in your calculator, what you're going to have. Okay, so when you punch this in your calculator, these are the values you're going to have. Now, we are done with everything here. Let's address what you have down. 1 over G23. So that is S44. So S44 is 1 over G23. You put your values. G23 is 3.20 times 10 raised power 9. 3.20 times 10 raised power 9. Then the last one is S55 and S66. So S55 is still value. The answer you get is still the same thing with S66 because they have the same value. So S11 and S16 is 1 over G12. So that is 1 divided by 4.40 times 10 raised power 9. And again, if you do it correctly, okay, so when you point that to your calculator, these are the values we have. Now, if you observe, what we are just trying to do is that we want to set each of them to have the same standard form. So in your calculator, we try to put it to be times 10 raised power minus 12. To set each of them to be times 10 raised power minus 12. We'll explain further why we want all of them to be in the same standard form. So if you do this correctly, this is what you have. And if you look closely, we omitted one, and that is V23 over E2. It's not done for V23 over E2. And V23 over E2 is S32. So S32, let's quickly do that, is minus V23 over E2. So V23 is 0.458 divided by E2 is 12.10 times 10 raised power 9. And when you do it, we are going to have minus 37.85 times 10 raised power minus 12 Pascal inverse. Okay, so we have written all the elements from our compliance matrix. Now what we just need to do is to put it back in. Remember we said there's a reason why we are keeping this to the power of minus 12. The unit of this is Pascal inverse because this is Pascal. The inverse of Pascal is Pascal inverse. Okay, so let's move to the next step. Okay, so when we substitute it back, what are we going to have? 1 over E1 will be what? 6.4. We are having times 10 per minus 12, right? So I can choose to put this, all of them are in times 10 per minus 12. So I can choose to group all of them. And at the back of my matrix, I put times 10 per minus 12. Why? Because all of them now have the same power. So I can just be writing the values I have here. So I have S11, 1 over A1 is 6.452. This one is, we quickly do that. You have minus 1.6. Okay, so when you've written that, you just substitute everything that you have here and put it back into the matrix, right? And since all of them have the same power, you can put it times 10 power minus 12 at the back. So we have done our step 2, which is to get our compliance matrix. So the last step is our step 3. What's our step 3? Is to find or calculate the strain. Remember we said that we are going to be working backwards. We're going to be working backwards. We first found the stress. We now calculated the compliance matrix. The final thing is to get the strain out of our formula. So what is the formula for strain? We know that it is what? The compliance matrix F multiplied by my stress vector. So what is my compliance matrix S? This is what I've gotten out of it. What is my stress vector? This is the everything for my stress vector. So when I multiply both of them, I should be able to get my strain vector. Now, if you look at it, this is 6 by 6 matrix and this is 1 by 6 matrix. To multiply both of them can be at once can be a bit long for you. So the easiest way to multiply is you have to take note of where my stress was applied. Where was my stress applied? In direction 2. So because it's applied in direction 2, every other thing is just not really necessary. You can just multiply the second column by this stress here that you have here, especially this particular one. What do I mean by that? Inside this one, I have epsilon 1, epsilon 2, epsilon 3. Now, we're supposed to have the shear strain 2, 3, 1, 3, and 1, 2. The reason why we are not including it is because my force was not a shear force. It is the shear force that will produce the shear strain. So in the question, we're just giving we're just giving normal force. That is, they gave us tensile. That's normal stress. So a normal stress will produce a normal strain, like you are seeing here. It will not produce shear strain. So the remaining shear strains that we normally used to have are zeros. So we have epsilon 1, epsilon 2, and epsilon 3 alone. So it is equal to, now my S, since the remaining ones are 0, my S is going to be strictly just these ones. Why? Because since the other ones are 0, when you use it to multiply whatever you have here, they will also be 0. Because these other 3 rows, they came from this shear strain. So because we don't have a shear strain anymore, they are zeros. So everything down this row, they are 0. So we just have only this one, these first 3 rows, because we are only picking our normal strain. So for the S, I'm only going to pick these ones. That is 6.452 minus 1.6 minus 1.6 minus 1.6, 82.64 minus 37.85 minus 1.6 minus 37.85, 82.64. So this is for my S. Now for the stress, look at our stress. So remember, we don't also have shear strain and we don't have a shear force. So because we don't have a shear force, all these stresses are 0. I'll just pick the first 3. So it is what? 0, 27.78 times 10 raised to power 6, and this is 0. Remember that this particular matrix is having times 10 raised to power minus 12 at the back. So even when you want to be using them one after the other, you must make sure that you include this times 10 raised to power minus 12. Okay, now what are we going to calculate? How are we going to calculate this strain? What we are going to do is, the fastest way to be able to calculate it is based on where my force is applied. My force was applied in the 2 directions. Since it's applied in the 2 directions, I'm only going to make use of the 2 column, the second column, column 2. So what I mean is, for me to be able to get E1, E2, and E3, I'll just do this times this, that is my E1. E2 will be this times this, that is my E2. E3 will be this times this. So what are we trying to say? Even if you choose to multiply them one after the other, we know how we multiply row by column. This one is timesing this one, plus this times this, plus this times this. You will still find out that you will be ending up with only the middle, because these twos are 0. Because this times this is 0, plus this times this, that's the only value you get, plus this times this, also 0. So at the end of the day, you will just be having the middle as your answer. So whenever you are giving this kind of question in the exam, you just have to focus on the second column. If the force is applied in my first, if it is applied in the first direction, so maybe somewhere here, and the remaining was at 0, my area of concentration will be the first column. So I will now use the first column and be taking it one after the other. This times this times this times this, just like that. So because in this question, we just have the second row that is timesing this one, because the force is applied in the second direction. I'm going to make use of just the middle. So my E1 will be what? This times this, minus 1.6. I remember that this column is having times 10 per minus 12. So minus 1.6 times 10 per minus 12 times 27.78 times 10 per 6. So E2 will be what? This one times this one, 82.64 times 10 raised to power minus 12 times 27.78 times 10 raised to power 6. Then finally, E3 will be what? Yeah, minus 37.85 times 10 raised to power minus 12 times 27.78 times 10 raised to power 6. Okay, so if you do all this correctly, what you'll be getting is, okay, so when you do it correctly, you will have all this. Now, this is not our final answer. Remember that the question asks us to find the change in length in the dimension. So we have to find the change in L1, change in L2, change in L3. So that's actually the last thing that we need to do. Okay, so we have to find the change in dimension. So remember, strain is what? Change in length over original length. If you can recall, that change in length over original length is our what? Our strain. So for me to get my change in dimension, it is what? The strain times the original length. So let's start for the first one. Change the L1. What will I have? Epsilon 1 times my original length. My epsilon 1 value is what? Minus 4.44 times 10 raised to power minus 5. What's my original length? My original length is 16 millimeters. Now you can choose to keep your answer in meters. If I multiply this by meters, the 16 in meters, my final answer in my change the L1 is supposed to be in meters. Why if you multiply this by 60 millimeters, my final answer will be in millimeters. So I choose to keep mine in meters, in millimeters. So times 60. So for the second one, change the L2 is what? Epsilon 2 times original length. That is what? 2.296 times 10 raised to power minus 3 times 60. And finally, change the L3 is what? Epsilon 3 times original length is equal to minus 1.0515 times 10 raised to power minus 3 times 60. So if you do it correctly, what you will also have, what you will be having is this. Okay, so when you do them correctly, these are the values you have. Now, whenever you have a minus, you have to attach a compression as the answer. So minus means that we are dealing with compression. Plus means that we are dealing with expansion. So here I'm going to have expansion. Then finally, for the last one, I'm going to have also compression because it's minus. Okay, so this is how to solve any question that you are given on composite materials. Be able to know how the material deforms. Now, what is it telling us? That in direction 1, in our one direction, it's compressed. In our direction 2, it expands. In our direction 3, it was compressed. So whenever you apply a force, you can be able to tell how that force deformed. Was there expansion or was there compression based on what we have done here today? If you enjoyed this video, please do it to like, subscribe and leave a comment. And if you find anything challenging, you can leave a comment there. I will attend to you. Thank you and see you in our next video.